2 o'clock, so you should go. Mr. Yo. Yeah. So I hope everybody's back. Okay. Right. So as I hinted to before, we'll continue. I want to talk a bit about shared arrays and some more, let's say, involved concepts when programming on the GPU. And for that, I've constructed an example, which is, again, rather simple and maybe trivial, but still it'll help in order to introduce some new concepts that we haven't seen so far. So we'll look at this code that I put there in this is exercise 02. The file name is rot.cu, rot for rotate, and there's 2 other files there, but don't worry about that now. Let's just take a look at the slides for now, and then we look at the code later. Okay. So so what that code wants to do is basically this operation here, where this I now can be a large number, and V, R, and S are 2-component vectors. Okay, so for each I, it's a 2-component vector. And so U looks like this. So what is this? This is basically, I mean, for those, I mean, I guess you should all be aware that this is a rotation matrix, right? So if you have an angle theta, you construct this 2x2 matrix using cosine of theta and sine of theta. Then the matrix vector product of this matrix on a 2-component vector, which has the top the x coordinate and the y coordinate, will give you the coordinates of the vector rotated by this angle theta. Okay, so so what does this whole thing do? Well, you have, if we have some large number of vectors, which I will call Ri here, and you multiply each one with this 2-dimensional matrix, then you will rotate them all by a given angle. And then adding this S will also shift them by whatever amount is shifted and give you a new set of coordinates. Yeah, just a second. Yeah, okay. Okay, so so if I write out this multiplication here, so right, so I have R on this side here, and I'm adding S here. Then if I just write out this equation here for the 2 components, so each I will have an X coordinate and a Y coordinate. So then, of course, this multiplies the X coordinate, this multiplies the Y coordinate, and you get this line. And then this multiplies the X coordinate here, and this cosine multiplies the Y coordinate there, and you end up this line here. Okay. Just put it up there. So just so that you can see it. So what does this look like? So if I start with, in this case, I have 5 of these random points R, right? So this is R0, this is R1, this is R2, this is R3, this is R4, and those are their coordinates, X0, X2, right? Okay, so if I apply an angle to them, so they're all being rotated by theta, okay, then they will end up there where the red points are, okay? So that's after I rotate. So if I didn't have this S at the end, and then I apply a random shift. So this shift could be anywhere, right? So it's just a random shift, which is different for each I, and then they end up there. And so the green points are my new coordinates with the primes. Okay. So that's what this rotation means, in case you're wondering. So this is just a transformation which includes rotation and a shift. Okay, so this code, what it does is it reads two files, and the two files include the array of R's, right, and the arrays of S's. These are the two files that are prepared for you. They're just some random numbers which represent the points in the circle and the shifts. So read them in, then you apply this rotation matrix to R and add the shift. So it does this operation and then writes out V to a file, the V's to a file. It doesn't need to write them out to the file for the exercise to be correct, but it just does it anyway. And similarly to before, in this file, this is done twice, right? So it's done twice, exactly the same thing. And we do it twice so that we now go to the second part and do what we did last time and port that part to CUDA. Okay. Okay, so what we want to do is we want to implement a CUDA version for this, what I call their second call. I mean, the second part, for this code, and we'll look at the code. And for the purposes of this exercise, each GPU thread will operate on one element I, right? So I want you to prepare this code so that each GPU thread takes basically one point, right? So 1 point applies the matrix and then shifts. Okay, so I am going to let you, in a few minutes, I'm going to let you do this yourselves. You should be able, given what we did before, you should be able to follow the same steps that we did for the AX plus Y operation, include CUDA runtime, and include the functions that we said we need. Write a simple GPU kernel and try and run it. And of course, very helpfully, at the end of the program, there's this difference being calculated, so you know you've done it correctly or not. Before I do, though, I just want to walk you through the code. So this is not EX01 anymore. So what I'm going to do is recall my copy command. So I want to copy the second exercise to my home directory. You should all be doing this with me if you have not already. I'm going to put a V just so that I see the files being copied. Okay, and these .bin files are binary files that contain the points, the arrays of the coordinates I was explaining. So points.bin is the R's we begin with, and shifts.bin are the S's. Okay. Yeah. So. And so now I will okay. Okay, so some functions should be familiar from before. So let me go down to main first. Okay, so there is you still provide the number of points you want to transform, even though these points are in the files. I mean, the files are, let me see how to So that means that there are, just doing this quickly. Yeah, so there's, okay, so the maximum you can make n is 128 million. Okay, because that's the maximum number of points in the data. But of course, you can run this code with a smaller n, and it'll just read the first n points. So that's fine, and just do the transformation for the first n points. That's, you can use that to do it quickly if you want to run it quickly and see what's correct. So this is your main program. It reads n, and then it allocates the array that will hold the r's, these ones, the array that will hold the s's, so the shifts, and then the two arrays, so v0 and v1, because we're going to do this twice and store it in separate locations. Okay, these are just this is just a function that I defined above, which will just read the n first points and put them in the array R. By the way, I didn't say that I'm reading it into this structure. This is my own structure here. This is called chords, and this is just, you know, it's just a C structure, where in the first element, it's addressed with a .x, and in the second element, it's addressed with a .y. Okay? It's just a C structure. Instead of having a two-component array at each point, just to be more readable, I have a structure with a two member elements. Okay, back down here where I left off. So we read the two. Okay, the angle here that I choose to rotate it by is 10 degrees. Doesn't matter, it's just 10 degrees. It's just something I chose. And okay, and then stopwatch, rotate, and then stopwatch again. Okay. So this will time how long it takes to do the rotate and the shift. Okay, so we'll go back and look at this function again. Look at this function once I finish off here. So this is the number of floating point operations that are carried out, and this is the number of I/O operations, and I will explain how I arrive at these numbers. But then at the end, just as before, it reports the number of threads and the achieved floating point performance and the achieved I/O bandwidth. And then it does the same below, just as in the AXP operation we did before the break, and then gets the difference. And also writes the coordinates out to a file, although, as I said, this bit is not. Okay, so let's go and look at rotate, the function that is actually doing the work. Here it is. So you pass theta and the two arrays R and S, and then we compute the cosine of theta and the sine of theta. And this is the operation I have on the slide, right? So cosine times the x coordinate of R minus sine and y coordinates of R plus the shift in x. Whereas down here, it is the sine of the x coordinate plus the cosine of the y coordinate plus the shift in y. Okay, so the way I just count the floating point operations is, you can see here that, okay, these are also floating point operations, right? Doing the cosine and the sine costs some floating point operations, but I'm assuming that n is so large that these do not really contribute so much into the calculation, right? Because you do n of these, and then you do, you know, 2 or 3. I don't know how much a cos or a sine costs, to be honest. It depends on the architecture. But whatever it is, you know, you know, orders of magnitude smaller than the number of floating point operations that you're doing in this large n loop. So we ignore these two floating point operations, and so we just count 1. Star here is 2, 3. The star here is 4, and then you have, you know, For each I, you do 2 times this, so that's why it's 8. So that's how I get, you know, this approximation of 8 floating point operations per iteration. For I/O, it's similar to before, but it is, I need to read one float. Yeah, I need to read the X here, I need to read the Y here, and then I need to read the X here. So far I've read 3 floats. But now when I come down here, I don't assume that you have to read X again and read Y again, right? So I assume that this is already read into some temporary variable. Compilers are good about doing this stuff. So in total, for each iteration, I need to read all elements of R, and I need to read all elements of S, and then write them out to out. So I need to access 6 floating point numbers for each iteration, right? Either read or write. And that's how I get the number 6, where I compute the bandwidth. Good. I don't think there's much more to say here, because read chords is straightforward. I mean, it's just an F read, the allocation stuff, etc. Right. So why don't I let you go ahead and try and port this to the GPU, and see how far we can get in. So it's my clock here says 17 past. So I'll come back here at 40 to 240, right? I mean, you can ask me questions, etc., but I'll be walking around looking at what the people here do, or if you want to, the online people can also ask me, but try and follow the steps that we did before in order to, you know, port the second part to the GPU, okay? All right, let's see.
I have a question.
Yes.
So in the OpenMP function, we have this cos and sine theta functions. So these functions have the same implementation within CUDA.
Sorry, these functions have the what? Sorry?
Have the same implementation. I mean, can the CUDA functions read functions from libraries that are within the main program?
Yeah. Oh no, there is a math library for kernels, so that's fine. You can call this. You can call this in a kernel.
Yeah. Okay. And when we include, for example, this math.h library, basically we overwrite any variable that is that we assign to cos or sine, right?
No, I think it's part of CUDA. Those are defined for the kernel differently.
Okay.
So, because you still need it to call it in the CPU function, right? So they just overloaded in the kernel, or they probably compiled into a different function in the kernel when there's a global in front.
Okay.
Two functions, sine and cosine, will run on the GPU.
Yeah.
With no need to change the name.
No. Yes, very good. Yes, now they should be chords. So size of should be chords, and you should cast the pointers to chords. Elaine.
Sorry, how do I know that I've done it correctly?
Say again. How do you know?
How do I know that I've done it correctly? I get the difference very small, the diff value in the end?
Yeah, 10 to the minus 15 or so.
Ah, excellent. Okay, thank you.
Good. Yeah. No. So you're calling it without any number of threads. The brackets. Yeah. Okay, I'll start slowly building this up. But if you still want to, if you're close to doing it, then I just suggest you continue, because that means you've probably covered the first bits that I'll say here. So first of all, I will add the CUDA runtime like we did before. Oops, no CUDA runtime. Yeah, okay. So that's the same thing we did before. Then I'm going to add this allocation function that I had in the other exercise. So this is what you also should have done. Open the previous exercise and just copy over this GPU alloc function. Oh, over to this one. If I'm doing something you want me to explain, then stop me. Okay, but so far everything has been like in the XPY version. Okay, so I'm going to save this function for last. Okay, so the kernel for this function, for the rotate function for last. So the GPU cannot read from files, right? So you have to use, as you did the CPU, I mean, the CPU reads from disk, and then the data that you want to process are in R and in S, and then those data that are now in memory, you need to push to the GPU memory the same way we did in the previous example. So don't try to call the read functions in the GPU kernel, right? They don't, the GPU doesn't know about file system and file IO. Okay, so first of all, we need to allocate our so-called device pointers here. So just like before, but now we should note these are not float anymore, but they're of this chords type, but that's fine. We can still allocate them as chords pointers. So it's GPU alloc and size of chords. And the same for S. And I also will allocate one for the V that will be copied back. Okay. Okay. And then I free them down here. Now which one is left? R. Okay. What else is left? I should copy R and S to the CPU. One copy. So the mnemonic again is dr equals R. The number of bytes is size of chords times n. And the direction is CUDA, and then copy host to device. And the same for S, right? V, I only need to copy back. So V can be uninitialized on the GPU, filled in, and then I copy it back when I'm finished. So I just need a minimum copy here. So this will be V1, right? DV, and then device to host. Okay, I think that the only thing left is to do the GPU kernel, right? So this will need to go away. Let me just clean up this stuff. So we're not using threads anymore. So let's just clear this nonsense here. Good. Okay, so all that's left is to define the, well, all that's left, yeah, is to define the kernel up there and then call it here. Okay. Okay, let's go define the kernel. So we said every thread will read, will do the operation on one element of the coordinates. So we will, let's see. So first of all, I just copied, well, all I did was copy the CPU version and fix the comment. Very important to have good comments in your code. Global, and change the name because it needs to be a unique name. Very good. So far, I think the arguments will be the same. So you come in and get the cosine and the sine again, it's fine. But now I want to get, as before, the thread index, right? The number of threads per block, locked in .x. The index of the block, and then compute the global index, same way I did before. So it's going to be I block times the thread. Oh. So now I know which thread I am in the whole block. And so now I can just do this without the loop. So IDX. Okay, any comments or questions up to now? Good, very good. All right, and now I have to fix this. I have to call it GPU rotate to put something here. And I have to make sure that these are device. And I need to synchronize. CUDA, what was it? Device synchronize. Okay. Let's say, so here I'll put int n thread equals, I don't know, 512 again. And then I will need n over n thread blocks and n thread threads per block. Should we try it? Let me see. Am I missing something? I don't know. Let's compile and see. Right, and now let's srun. Start with something small. Okay, there we go. So my CPU version excuse me while I fix a bit the no, I won't. Anyway, I won't. Yeah, so a difference of about 10 to the minus 15 is reasonable because it's a single precision and it's the limit of single precision. Accuracy, what else should we say? On the CPU, we get about 50 gigabytes per second. We said the number to compare with is the 130, and you can probably get a bit close to 130. If you go for larger array sizes, let's try that. But in general, you won't see the kind of performances that you got with the simple AX plus Y operation, just because here the memory access patterns are a bit different. Okay. The GPU gets you about 650. So this is a good performance to start with, right? It's much higher than 50% of the peak bandwidth, but we're wondering maybe we can get close, okay, to the 900, which is the peak of the GPU. Okay. Does anybody want to ask me anything about what I did here?
Okay, I have one question.
Sure.
Yeah. So the array where you store when you want to store the output, so DV, I somehow also did the CUDA memory copy, the empty array, because I thought that otherwise the CUDA will not be able to.
Up here.
So does the GPU alloc already is provide, like, does it do the job already? So I don't need to do the CUDA mem copy of the empty array.
Just so I understand. So here you also have copied.
Yes, I copied the empty array basically because I thought that in order to, let's say, be able to write the output, I need to put an empty array in the function and then I get this array back as an output.
No, so
No.
you don't need to do that. So here you allocate the memory on the GPU, and the fact that it is uninitialized does not affect your result, right? So the fact.
Okay, so this part is already doing the job, so I don't need to copy the empty array.
This is allocating it. If you needed it to be set to 0, for example, for some reason, so if you needed V to be on the GPU and have all the elements set to 0, then you would need to do it. You would either need to have a kernel that sets the elements to 0, for example, or you would need to copy a 0 array from the CPU, from the host to the device. But in this case, right, you're just setting it. So here you are setting it to a value. So you don't care what the original value of the array is. Because you don't care, all you need to do is allocate it. Yeah.
Okay, thanks.
Okay. Yeah.
In the previous example, did you leave out CUDA device synchronize, or I missed it?
Yeah, at the beginning I did, and we got this.
The first example.
At the beginning, I left it out. In order to show you that when you do your timing measurement is completely off, because you're only timing the time you need to invoke the kernel, and we got something like thousands of gigabytes, per second, and I said, yeah, you need to add it because this, to block before you measure the time. Yes. Okay. Okay, so if there are no more questions, then I'll shift to the continuation of this exercise, which is to show you how this can be improved a bit. So this performance. Okay, but it's important that you understand what we did here before we do that. Okay. So let's see what we have. Where is my win? There's my, okay. Let's move on here. Okay. Yeah, okay. So this is something that you can do, but when you're back home, you can have the number of threads be another argument that you give, a command line argument. And so you can do like a loop and scan the optimal number of threads. This was just to see what is the best performance we can get. So yesterday, for example, the best I got was 670 or so gigabytes per second, which is about 75% of the 900, which is a peak. And I'm going to answer this question with a yes, and I'll show you how can we do better. We can do a bit better. Okay. So we're doing something here, which I said in the last exercise is a bit suboptimal. Do I have a, yeah, okay. So if you, I'll go back to the last exercise. I'm just going to move back. Okay, so remember this picture, right? So now the 0th element of the array is the x coordinate of the first element, right? And then the element 1 of the array is the y coordinate of the 0th element, right? Because it goes, the way it's laid out in memory is x, y, x, y, x, y, x, y, right? So that's how the structure is laid out in memory. And what you're doing with your code is you have the 0th thread, thread 0, for example, is reading both the x and the y coordinates of the first element of the R, and both the x and the y coordinate of the element of S, of the first element of S. And okay, so it's not as bad as we did it in the first version of this AX plus Y example, because you don't have one thread reading, you know, a big chunk of continuous memory, but it's still slightly suboptimal because you have the same thread reading two adjacent elements of the array. Okay. So one way to fix one way we want to fix this is to have each element, each thread, sorry, operate not to get the result of one of the coordinates of one of the elements of the array, but to just get one component of the coordinates. Okay, so let me just say what that means. Okay, so instead of each thread operating on one point, consider each thread operating on a single component of the coordinate, right? So now you'll need twice the threads because now you have twice the components. But let's see if this is better and what you would need to do it. So in other words, you want the even threads to compute the x coordinate of the result and the odd threads to compute the y coordinate of the result. And if you want to do this efficiently, we need to also use shared memory. Okay, so fast memory, which all threads in a single block can access. Okay, so this is the first time I'm going to show how to use shared memory, but in general, shared memory is declared with the shared attribute. So in your kernel, it's like you allocate any other array, but you add this attribute shared in front. And that means that in the block, all elements see the same elements of this array, okay? Whereas if I didn't have the shared attribute in front, then this float array would be different memory for each thread, okay? But now with the shared attribute, this memory is shared between the threads. Okay, so if you do it like this, you need to know size at compile time. So size needs to be a number, which when you compile the code is known. So it's not something you can pass from the command line. If you're going to do it like this, there is a way to dynamically allocate shared memory, which is a relatively recent CUDA feature, but we won't be covering it now. So what we will see, this size of the array will be determined. Okay, but below, okay, so having said that, below I'll show you a bit what we want to do. So this looks a bit weird, but I'll try to explain it. So here I'm describing what we're computing and which thread will do this. So this is how we want to end up doing it, okay? So the x coordinates of the element I, right, +0, I, within this block, right? So we have a block which begins from element I. So the x coordinates of this first element, we want it to be computed by thread 0. Okay, so this is the element in the array we want, and notice now that I'm assuming that our arrays now are not don't have a .x and a .y anymore, but they're just one long array where the even elements are what was the .x component, and the odd elements are what was the y. So we've cast this, instead of an array of n coordinates, we've cast it into an array of 2n floats, okay? Because that's what will make this optimization possible. Okay, and the same for R and the same for S. But notice the pattern here, okay? So you need the even element of R times the cosine minus the odd element of R times the sine plus the even element of S. So the S's are nicely lined up here, 0, 1, 2, 3, 4, 5, right? So the thread 0 will get S0, thread 1 will get S1, thread 2 will get S2. So as far as the S's are concerned, these are nicely aligned with, with the thread number. But the R's needed by thread 0 contain both an R0 and an R1, right? And then the R's needed by thread 1 contain both an R1 and an R0. So this guy, so these two guys, thread 0 and thread 1, they need both element 0 and element 1 from R. Just of the way the pattern that this matrix multiplication of U times R is, that it takes these two components and mixes it. Okay, so these two threads are mixing their components, and then also these two threads are mixing their components, right? So thread 2 needs the second element of R, but also the third. And see this in the same line. Whereas thread 3, thread 3 needs the third and the second element of R. Okay. Okay, so this is an example of a kernel where the operations are not exactly the same for each thread, right? So even threads need to do one thing, and odd threads need to do another thing. Okay, but it's important in a GPU kernel to have all the threads do the same operations. Okay, so, well, yeah, okay. This is not an exactly accurate statement, but for the purposes of this exercise, it's important to have all the threads do the same operation. So just to say, more explicitly. In other words, you need to avoid constructs like this. Okay. Why? Why do you need to do that? Okay. The reason is that the way the GPU architecture works is that a group of continuous threads needs to execute the same instructions, and that group of threads is in this case, this GPU 32 threads. Okay, so the threads with index from 0 to 31 can only do the same operations in parallel. Can only follow the same instructions in parallel. If you reach an if statement like this, okay, if I threads mod 2 equals 0, whatever is in here will actually be done by all the threads. This, even though the thread will have an index 1, it'll still go through this. It's just that the hardware will later on discard the results for the odd threads. It's just how the architecture works. You cannot branch continuous threads into different branches. The result will be that the even threads will go in here and keep the result of whatever's in here. The odd threads will also execute these instructions. It's just at the end that the GPU has machinery to invalidate them. So if you have something like if I thread mod 2 equals 0, do something else, then basically those two blocks will be done one after the other serialized, because those threads have to do the same instructions. Okay. Okay. And that will result in inefficient code. Does anybody want me to repeat that or say something again? Okay. And we'll move on. Okay. So in order to make these changes to our code, okay, first the simple things. First, we need to define this max threads, which is going to be the size of the array, which we said we need to know at compile time. So we just define this constant to be 1024 at the top of the file. Okay, then when we call the kernel, we need to change it to use twice the number of blocks, right? Because we said now that each thread will not be operating on a pair XY, but will be operating only on an individual component, which means that now we need twice the number of threads, and we implement this by doubling the number of blocks that we will use. Okay, in the kernel, we will define the shared float array with the maximum number of threads. And we need this shared array var because different threads will need to access the same elements, right? So we said thread 0 will need to read R0, but also R1, okay? So whether odd or even, each thread needs to access both the X and the Y coordinates of R, right? So we need to read once all the elements that will be used in this block into the shared array, and then access them from RR. So we need to do something like what's shown here, okay? So if let's say the number of threads is the maximum, so it's 1024, then, so this piece of the kernel here will, well, first compute the index, the global index of this thread. And then this is another form of this implied loop, where each thread is responsible for loading one element of R into the shared array, okay? So after this line, the shared array RR is filled with the X and the Y coordinates of R, right? So the even elements of RR are the X coordinates, and the odd elements of RR will be the Y coordinates. So this way the loading is done in parallel. Each thread reads in one component of R. Okay, so let's do this together just now, just to make sure we're on the same page. So I'm starting from this version of the code that I showed you before, that hopefully you also managed to get to some extent. And so now, excuse me. And so now I want to here, yeah, I want to change this so that so that I can do this more optimal thing, right? Okay. So if you want, you can follow along. So the first thing is that instead of having these device pointers be chords, I want them to be float arrays with twice the number of elements. Okay, so that's easy enough to do. I just make them float with twice the number of elements. Ask them to float so that it doesn't complain. So that's float 2. Well, that doesn't matter. Whether it's size of chords or 2 times size of float will be the same, but in any case, maybe it's better readability. Okay. This bit can stay the same, right? Because as far as the GPU and the CPU concerned, these are just bytes, 4-byte words, one after the other. So if you copy n chords or 2 times n floats, it's fine. Okay. So the same is true here. And let's see. So if I go up here to my GPU kernel, then these should also float. Okay. So actually, maybe it's useful. Maybe it's a bit useful just for, you know, just to understand a bit what's going on. So if I weren't going to change anything else, right? So I still have n over n thread blocks. So I still have n threads per, what is it, per block? I still have n threads per block. And so I still have one thread per X and Y coordinate, right? So I haven't done the splitting yet. So if I were to just come back up here, then these arrays now, this out has twice the number of elements, right? Because it's not a chords anymore. Okay. And so here I would, because it has twice the number of elements, I would do something like this. So this corresponds to the, and then I'll just put a 0 there just to make sure that I understand. Okay. So this is now what was before out idx.x, right? But now out is no longer an n-length array, it's a 2n length array, right? And so the even and the odd elements are the X and the Y. Okay, so this is an intermediate step to what we want to do. And I'm just doing it here just to show that, that here you would need that, and you would need +0. Okay, so maybe this reveals a bit better the pattern that we're trying to get away with. Okay, right. So this is what was ridx.x before, and this is what was ridx.y before. And again, here you have what was ridx.y before, and here you have what was ridx.x. Okay, so this should, I didn't try this actually before, but I just thought of doing this now. But this should do the same thing as unless I screw that. Yeah, I did something wrong. Okay.
Can I have a question?
Yeah, yeah.
Why this time when you call the GPU rotate, you don't write 2n divided by the number of threads?
I don't need twice the number of threads, do I? Because each thread is so each thread so thread 0 here will compute the 0 and the first, and then thread 1 will compute 2 and 3. This is .x, right? It should have been .x and this .y. This is how I had it above. Yeah, okay. Yeah. Thank you. Okay, okay, we're back. All right, so so this now is just doing the same. Eventually, we managed to do the same as we were doing before. But now I want each thread to operate one of these lines, right? So now is where I want to make the change. Okay, and yeah, so so how do I want to explain this here? So this is how I want to explain it. So now I would go down here and say I need twice the number of blocks. So I do this change that feature suggested, but now I do, yeah. So now each IDX is, if it's odd, it's going to do this line, right? And if it's even, it's going to do this line. Sorry, the other way around. If it's even, it's going to do this line. And if it's odd, it wants to do this line. So this is wrong. So now I want you to, well, okay. So first of all, let's do this first bit here. So we have a shared load. Oops, not out there, here, yeah. And okay, and then just define this up there, 1024. So that's just the maximum number of threads. So it's the maximum size that this matrix will have. Okay, and now I do this. Okay, so what does this do? Again, instead of now, so now I can refer to this RR array instead of referring to this R array. So every time, so when I do this, so if I'm an even thread and I do this line, then I need to read both, you know, the even R and the odd R from memory. So I'll be taking, you know, both elements from memory. Whereas if I'm an odd thread, I will again need the same two elements. Okay, so I want to save these double reads by reading once the array. Each thread will read one element of the array like this, and then store it in this smaller RR array. And then I want in the kernel to access just the RRs rather than the R elements. So this is this red memory that was in the diagram, which is faster because it's defined as shared. Okay. So, so far we have not done any part of the kernel, but if you consider this piece, okay. So if I do this, so float RS is S of IDX plus CT RR of I thread. Then what have I done? Well, if I'm an even thread, right, then this achieves this bit plus this bit. Okay, so that bit is done. If I'm an odd thread, then this will achieve this bit plus this bit. Okay, so I'm just gonna rearrange this a bit just to make this clearer. Okay. So what I've written here in this line, well, independently of whether I'm on an even or an odd thread, I've achieved this, which is the same regardless of whether I'm an even or an odd thread, right? So I just identified that these pieces are the same for even and odd threads, and I added them. But now this RS is only the partial result. So now is the difficult bit. I need to, if I'm an even thread, subtract this from RS, or if I'm an odd thread, add this to RS. Okay, and here's where, okay, that's just saying what I said. So the operation is still complete. What we've achieved is just that bit, but now we also want to subtract this from the one or add this to the other. Okay, so there's not a unique way to do this, but remember what you want to do is not use an if statement, but one way to do it is to define this switch variable here. What does this do? So the ampersand is a bitwise end operation, meaning that I thread and 1, so what I have here in the parenthesis, this will evaluate to 0 if I thread is even, or 1 if the thread is odd. Okay, and if this is even, then this is 0, and so this switch is 1. Yeah, 1. Whereas if the thread is odd, then this whole parenthesis is 1, and so 1 minus 2 will give you minus 1. Okay, so this is what the whole thing achieves. If I thread is even, odd, then the switch will go 1 minus 1, 1 minus 1. And this is exactly what I want in order to determine the sign, to flip the sign, whether the thread is even or odd. So now the part that is remaining can be written like this. Okay. RS equals right? Because I thread plus this SW will either be ithread +1, which means if it's even, it takes me to the next one, or it'll be ithread -1 if ithread is odd. So if it's odd, it will take me to the previous one, right? Okay, so then you just have to put it back, put RS back into out. And we should be done. Did I remember to put 2 times here? Yes, I did. And let's see how much better this is. It won't be that much better, I should say. But it's a decent, it will be, I think, higher than 750 or something. Yeah. Okay, so we changed a bit the order of the operations, so the difference won't be exactly the same. But this is again floating point precision. And okay, we got about 100 and so gigabytes per second more. So this is clearly running slightly faster, not dramatically faster. But still, this is an example of the kind of tricks you need to do when you program GPUs if you want to make sure that you're getting, that you're getting all the threads to do the same thing using the shared memory like we are here. So if I weren't using the shared memory here, then I would have to have an R here and another R here, which would mean I'm reading, I would need to read the even and the odd elements twice from memory. Okay. That's.
I will repeat that question.
No, yeah.
For the, you don't need to synchronize the threads before using RR element, which is fetched from a different thread.
Yeah. So the question is actually very valid as far as I can tell. So there is a so-called, that you could be running into a race condition here. What would be the race condition? So, for example, the 0th thread here is reading the 0th element of R, right? And the first thread here is writing the first element of R and so on. And since we have no guarantee of the threads running concurrently line by line of code, right? There's no guarantee. Then there is a danger that, for example, thread 0, right, comes to this line, which is reading RR of 1 before R of 1 is actually written by the first thread there. So, so what I would need to avoid this is the first time I need to get an element from another thread is to add a sync without the H. Okay, so this is basically, if you're familiar with MPI, is like a barrier, right? So the threads will block at this line before they move on to the next line. So this guarantees here that RR, this RR array will be filled with all elements before anybody needs to access any element other than RR. So you don't need to call it up here, right? Because the element that is being read here is of the same thread that's actually filling it in. So there's no worry of a race condition screwing up your result here. But you do need to call it here in order to guarantee that when, for example, thread 0 tries to access RR of 1, that, you know, thread 1 is not still somewhere up here and hasn't actually filled in this element into RR.
So it's the equivalent to MPI weight equivalent.
I would say of a barrier. It's equivalent
Okay,
to
okay,
MPI barrier.
barrier,
Yeah. Yeah. Yeah.
It might not be needed because we either have an odd or an even thread, 0, 1, then 3, 4, which is
So it should be that
they
they're all
won't
in
be
the same
crossing
warp.
the 32-bit.
It's all in the same warp.
Yeah.
Yeah. So actually, I haven't seen any risk of a race condition. Strictly speaking, though, you might go to architecture with, no, you can't go to architecture with different warp. I don't know. But maybe it's safe, more safe to have it. But yeah, probably they'll all be in the same warp, and there's no risk of condition there. More questions? With the sync threads. You think this will kill it? Oops. So much. And actually, how many threads am I using here? Actually, I think I saw. Yeah, I think here using something like that is slightly better. I'm not sure why. There's a break now, right? Yeah. Oh, no.